So how do you deal with high dimensionality? Well, one way which we've seen extensively is by extracting features out of data. So that's something that requires domain knowledge. And what you do there is you start with your high dimensional observations, say your bitmaps or your text, and you apply some knowledge about the domain to create features about that data, right? So in computer vision, for example, you use something like SIFT. And the reason you use that is that is a form of zeroing in on the parts of image that are important and ignoring most of the image. Or you have color histograms. It's a very crude way to represent pixels, but it's a lot less, it has a lot smaller dimensionality. And we know that it makes sense because object appearance in images tends to be correlated with certain patterns of color histograms and certain patterns of texture histograms. Right? So, but to do that, you need to know something about the domain. So if you knew nothing about images, you wouldn't be able to design SIFT features. Another way to deal with high dimensionality is to make some sort of assumption about your dimensions. So the independence assumption, for example, something that we did in naive Bayes, what that says is I'm going to count my observations separately along each dimension. So even though I have a two-dimensional data set, when I count the frequencies for attribute x1, I'm going to count them ignoring the value of x2. So in effect, what I'm doing is for every possible value of x2, I'm hypothesizing the same count. That's what independence looks like. And what that does is that propagates a lot more observations to a lot more regions. But I'm losing the ability to model correlation between the two attributes whenever I do that. What else can you do? You can assume smoothness. So that's something that gets done implicitly by the KNN algorithm and by the kernel algorithms when we talked about that. The assumption there is if you have nearby regions of space, they should have similar class distributions. So if I had an observation of blue in that middle cell, this means that I should increase my probability of seeing blue in the neighboring cells. And if I observed red in that cell, then I should increase my probability of seeing red in the neighboring cells. So you're making a smoothness assumption. Nearby regions in space should have similar distributions of colors. Another thing that people do is they sometimes assume symmetry. So symmetry means you flip the attributes, you flip x1 and x2 without flipping their values, right? So the value that you previously observed for attribute number 1, you now observe the same exact thing for attribute number 2. So you just swap the dimension. So you get data that will be symmetric around the diagonal, and that will also increase the counts that you get in various regions of space. Now, if you don't want to do any of those things and you still have a high-dimensional data that is problematic, the solution that is left is to reduce the dimensionality. And reducing the dimensionality means I had my own dimensions, my old attributes, and I'm going to come up with a new set of attributes, and there's going to be a lot fewer of them than previously, but they will still somehow reflect the good properties in my data.